Good afternoon, everybody. It's really an exciting time to be in semiconductor industry. It took us about 70 years to get to a $500 billion business, and the forecast is that within next 7 years, we are going to double it to a 1 trillion or something above that. And it's amazing how these things ramping up, and the demand for semiconductor is growing so fast. However, only a tiny bit of this $500 billion or that 1 trillion is HI, or heterogeneous integrated solutions, for many reasons that I'm going to talk about later. And it's interesting how much money and how much funding is coming to semiconductor research, unprecedented as far as I remember, or maybe Sematech was the last one that we remember in the 80s, but what we see today is not even in that range. It's a much bigger investment across the board, all over the world. So the side benefit of that, we don't need to explain to our families what we are doing for a living anymore. It's in the headline news of Wall Street Journal, Economist, New York Times, everybody's talking about semiconductor. But what makes it so exciting now is that for many years, since the birth of CMOS, we always looked at the next node as the savior of all design problems. If you cannot get it low power enough or don't get enough digital density, wait until the next node comes in 2 years, 2.5 years, whatever years, and depending on how you count. But now we see that in analog and mixed signal specifically, there are many vectors at play that makes it really exciting because it's highly diverse in terms of applications, in terms of technologies. We talk about many technologies later, which is beyond just CMOS, but also emerging technologies like quantum sensing. And I'm not talking about cryogenic. I'm talking about room temperature quantum sensing by using technologies like nitrogen vacancies in the diamond and technologies like that. Biosensing is becoming a huge opportunity. Again, it's not sitting on top of the latest node of technology. In fact, in many cases, you need to have combination of technologies. And silicon photonics, and even chip scale atomic clock, and so on. So many vectors are at play which need to come together in a very efficient and cost-effective solution. And in many cases, actually, we noticed that cost is the driver of innovation and how to make things more mass product and then come up with ideas that are beyond and above what we are doing today. So there are many elements when it comes to mixed signal and analog, from precision, biosensing, industrial sensing, photonics, MEMS, RF, and so on. And since we are living in an analog world, we are sensing, we are smelling, seeing, hearing, and even transmitting analog signals. We need to be very efficient in power density, in interconnect, in thermal capacity, parasitics, and so on. And there are many angles to that. We don't have time to go through many of these, but I'm going to refer to some of these vectors later in my talk. These are some of the ideals we have in analog and mixed signal, how to push the envelope so much that we can achieve a lot more than what we are doing today with our electronics. For example, a power density of 10 kilowatt in a cubic inch. That is kind of power density in a lot of these systems that we are working on today, including some of the data centers, power management, or high resolution, high speed gigasamples that can really fit a lot more gigabits per second per millimeter square, or having a lot better 5 to 10 times higher picojoules per conversion in our data converter. Think about some of the today's solutions in communication requires less than 50 femtosecond jitter, down to 10 femtosecond, almost the quality of chip scale atomic clock on chip. And we're almost there. And it's all kind of like MEMS-based type of solutions that you can integrate with some of your high-performance solutions. And when it comes to RF, LNAs, PAs, integrated passives, a diversity of technologies. And it's interesting how dynamic they are, and I'm going to refer to some of those later. And on top of that, what's happening on the back end of the line that you can put on top of the typical CMOS. Could be your basic CMOS DSPs or some advanced processors or anything else. And also we have some examples of that. So these are the trends that are really makes it very exciting when it comes to heterogeneous integration. Look at the red line here. That is, or maybe blue line, that's a scaling of the silicon. And you can see it's slowing down. Now you call it, it's done or about to be done or whatever format you're saying, it's slowing down. But on the other hand, the red line, which is the scaling of the package, is speeding up. So we can offer a lot better density of interconnects. We can offer a lot better integration and lower parasitic in a lot of packaging. And that is the revolution of HI that is we are seeing today at low cost, and it opens a lot of opportunities for bringing the right technologies together. So here is an example of the kind of benefits we see. For example, if you are designing an RF, you don't see much benefit going below 22 nanometer kind of technology, because then you are going to get hit with a lot of voltage headroom and noise issues. But in many cases, we had to, because the rest of the system was driven by the density of digital transistors, so we pushed it down. And ideally, if you have a chance to bring a silicon germanium bipolar transistor with a back-end CMOS in the deep submicron, would be a lot more efficient system. But people don't go to 3D for the last 30, 40 years unless they have to. Because monolithic is cheaper, monolithic is easier to produce, and there is a cost penalty when you do this MCM in many of these systems. So it is changing now because we are getting to the limits. The yield is another issue. We can improve the yield significantly, but decoupling some of these trade-offs, finer bump and pad pitch, and flexibility of these systems. And of course, there are challenges. We need interconnects. We need to move toward 1 milliwatt per gigabit per second on some of these interconnects. We need to improve the efficiency, density, and so on. So let me start with power management as an example. Here is an outdated chart, but interesting. In 2005, only 30% of entire energy in the United States had anything to do with semiconductor. By 2030, 80% of the energy is going to be semiconductor conditioned. And that means about 3 terawatt hours of saving based on what we see. So there's a lot to gain there. And the chart here shows that today, the energy used for data center is about a couple of percent of the energy usage. It's going to go up to 20% with all these generative AIs and with all the cryptocurrencies and all that stuff. So you can see that the power and energy management continues to be a challenge. We don't have much time to go through the whole thing, but what happens in power is pretty much similar to what happened in RF about 10, 15 years ago. Remember, we went from heterodyne, multi-stage down conversion to single direct conversion. Same thing is happening, and now the stages that we have, we need to reduce it in order to maintain the efficiency, but the integrity of the power. Power for these high-performance GPUs and CPUs is very challenging. First of all, it's moving up to 1,500 amps. Drops below 1 volt. Can you imagine the line you're getting in your house for the entire house is about 100 amps or 200 amps, depending on how big your house is. We're going to have 15 to 2,000 amps on the board feeding these processors, and it's dropping below 1 volt, and it has to be within 5 millivolts of accuracy, and it has to wake up very fast. It's like when you are in a meeting and you're tired and you're taking a short sleep, but you wake up very fast when you hear the right voice. That's kind of system you need here. You don't shut off all the sensors. You put it on the standby. So you just hear what you need to hear, and then you wake up. So we need to kind of have all this intelligence built into these systems. So we are using GaN today to drive this density in a totem pole technique, which is kind of like a hard switching and can give you almost 30 to 50% of power density improvement. And another thing that's happening in data center and automotive is 48 volt is becoming a very exciting intermediate voltage for many reasons. But to give you an idea, a typical rack today is going to have about moving from 4 to 5 kilowatt to 20 to 40 kilowatts. And that means we need to have a lot of improvement in the efficiency and a lot of improvement in the packaging, which I'm going to show in my next slide. This is a typical packaging for power delivery of the GPUs. No longer lateral, everything is vertical. It has to be integrated. You have to use the right copper pillar and right interposer, active interposer, to achieve 1,500 to 2,000 amps, and with high DIDT and all the performance requirements that you have. Let me briefly talk about RF. RF is kind of interesting, RF and photonics. As we get closer to this slowdown of scaling, a lot of new opportunities are popping up that is showing that HI can offer not only performance advantage, but even cost advantage. And I'll show you how. This chart, I'm sure you have seen it. Silicon germanium still is the king of up to 337 dBm, up to about tens of gigahertz. But we see that gallium nitride on silicon is becoming very competitive. On the PA side, the same story. I mean, we see that gallium, on the PA 37 dB, on the LNA is about 4 dB noise figure that we need. And for some of these applications, silicon germanium is outstanding in terms of performance. But we get to very high performance, then indium phosphide and other technologies are going to show up. But the borderline is kind of variable. They're changing, and we see that these borderlines are quite dynamic. And I would say that GaN on silicon has some of the widest applications here because it has potential to go to 300 millimeter fabs and cost down and performance high. And you don't need the latest lithography. People talk about 90 nanometer or that range. And the FT that you can get in terms of the SiGe process by CMOS can go to 650 gigahertz. And that is kind of systems that you can put all in one package. Here is the chart of, you see that SiGe, CMOS, 3.5, and a whole bunch of waveguides that are feeding the antenna on chip in order to reduce the parasitics. And we have this working in a system. I skipped that one and show it in a radar system. We did the first generation of radar, all CMOS. I remember first radar we did in my graduate study. It took $1 million to develop. This is like orders of magnitude cheaper, all on CMOS. But in order to improve the Doppler, you cannot just rely on a crystal unless it's very expensive. You have to bring MEMS resonators. And in order to get the highest efficiency, you need to bring silicon germanium or GaN on silicon to improve the transmit power. Just let me briefly talk about what's happening in 6G. I mean, 6G, hopefully, it's going to be more than just additional bandwidth and additional number of antennas. It's going to be a totally different system in terms of the pencil beams that have maybe changing the concept of cellular completely. These are some of the promises. But interestingly, it's going to have massive amount of modular RFs. We call it front-end modules. They require to either do analog or digital or hybrid beamforming. And for that, you need a range of technologies that is coming from passive integration all the way to RF, I mean, for front-end PA, LNA, and switch, and some of the filters that could be really high-performance filters based on some of the MEMS resonators that we see in the industry. So back to my chart, let me briefly talk about what's happening I have to touch a lot of topics quickly because we have this analog mixed signal, and it covers a lot of that. Photonics on silicon is very exciting, but it's very small today. It's pretty much limited to, I mean, some of the market estimates is showing $1 to $2 billion out of that $1 trillion range. Why is that? I mean, mainly we see the issues. It's not just integration of photonics and silicon. We see that some of the fundamental issues like fiber coupling still is expensive enough that limits it to applications that they have to have it, like data centers. But other applications are still require some more advanced research. And some exciting stuff is happening. V-groove on silicon or silicon nitride and some of these things that people are working on it, but still not there. Thermal management is a big deal because, as you know, some of these Mach-Zehnder filters and modulators requires very careful temperature management. And when you have a wide range of temperature, it becomes a much tougher challenge. New materials, lithium niobate, looks very promising. And again, we need to get lithium niobate to the scale that we can offer low-cost, high performance, and interconnect bandwidth, and so on. But again, the combination of many technologies and confluence of many technologies can come together to bring the photonics on silicon to a new stage and more than just niche markets and also to mainstream. One area that I'm personally quite optimistic about, and we have examples to prove it, is post-CMOS fabrication, meaning that back-end-of-the-line technologies that you can grow the materials in the temperature that is compatible with CMOS around 500 degrees, and you can offer some functionalities. Today, we have a range of technologies we have already developed on back-end of the line, like sensors, photonic array sensors, MEMS sensors. But there are some opportunities. You can use metal oxide active devices and 3.5 on CMOS. I'll show you one of the sensors that we developed, and it's been around for a while. It started in DARPA. It took us a while to get 2 million mirrors on a single chip. I mean, it's been around for quite a while. This is the DLP digital light processor, and it was developed on top of an SRAM with aluminum oxide layer, and on top of that, we developed these 2 million mirrors that can switch for 2 billion times cycle without any latches or any issues and reliabilities. Took us a while, but these are examples that you can take any piece of silicon and do some really cool stuff at low cost and not worrying about interconnect and some of the issues that we have in a traditional HI. So HI is an exciting opportunity, but it takes a lot of disciplines coming together to make it reality. The concept has been around for quite a while. The key is that how to optimize it by bringing these pieces together and make it a mainstream for a lot of these applications. Thank you very much for your attention. And that concludes my talk.